All right, so in summary, these are the different options for internal energy, heat, and work. Okay, if your Q is positive, that simply means that your system gained heat. Therefore, your surroundings lost heat. Okay, if the Q is negative, then that means your system lost heat to the surroundings. Same goes for work. If the system has work done on it, that's a good thing. Okay, if a gas is compressed, that means work was done on the gas, so that will be a positive work. If the system does the work on the surroundings, well then that's negative. That's the same as losing heat. Energy is exiting the system. If it loses heat or if it does any work, it'll be negative then. Now, to figure out the sign for the delta E, the change in energy, you simply add your Q and your W together. If the answer ends up being a positive number, then there was a net gain of energy by the system. If the answer ends up being negative, well, then it means there was a net loss of energy by the system, which is exothermic. Positive Q's, W's, delta E's, that means endothermic, energy entered. Negative means energy exited. Okay, so endothermic and exothermic processes, they are just the opposite of each other. An endothermic process is one that absorbs heat from the surroundings, so that'll be a positive delta E. An endothermic reaction, because it's absorbing heat from the surroundings, and we are the surroundings, so they feel cold to us. So when you hold one of those disposable ice packs in your hand after you snap it, so the chemical reaction can get started, it's an endothermic reaction occurs that pulls in heat. Where does it pull the heat from? You. Okay, and so it feels cold to us, remember, but cold isn't a thing. There's just the lack of heat. All right, so if you've ever done the baking soda and vinegar reaction, oh, ignore the typo there. If you've ever touched that, you know that that is endothermic. It gets cold. All right, on the flip side, exothermic processes transfer heat to the surroundings, and us being surroundings, we feel that heat and it feels hot to us. Those have a negative delta E. Methane burning in your furnace would be an example. The potential energy stored in the bonds are converted into thermal energy, heat that gets piped throughout your house. Okay, so the exchange of heat between the system and the surroundings. When heat is absorbed by the system, we call it endothermic. When it's released, we call it exothermic. Okay, so here we have a different symbol, delta H. H stands for enthalpy. I'll explain what that is a little later. If the delta H or delta E is less than 0, that means it's negative. It's exothermic, heat exited. Now, if it's greater than 0, positive number, then that means heat or work entered, energy entered the system. That's endothermic. All right, here's another table summarizing the different signs that are possible for Q, W, and delta E. I've said all this already, but you may want to pause and look at this. It summarizes it well. And videos that don't work anymore. All right, now into an odd subject that I think I brought up briefly at the beginning of the year, state functions. State functions are simply properties that are determined by the state of the system, regardless of how that condition was achieved. Well, that's clear as mud. Examples of state function are energy, pressure, volume, temperature. For example, here, the elevation of these two hikers is a state function. The change in elevation is a state function. They both increase the same amount of feet here. Or, well, this is science, so I better say meters. But the thing is, one of them covered much more distance, right? So distance is not a state function. Change of elevation is. Okay, so state functions, it doesn't matter how the change occurred, it's going to be the same either way. So whether you take the blue route or the red route, the change in elevation was the same. The amount of work they did, not the same. Red guy did more work. Amount of distance covered, not the same. Okay, so those aren't state functions. Energy, pressure, volume, and temperature, those are all state functions, because it doesn't matter how you change, like the volume, whether you increase it from 2 liters to 5 liters all at once, or you do it in a series of steps, the change in volume is the same. Temperature, whether you slowly increase the temperature or do it very fast. If you melt the ice cube, then refreeze it, kind of a thing. It doesn't matter how you get there. State functions are always the same. So here's another way of looking at it. Height is potential energy. The potential energy of the hikers is equal even though they took different paths. So state functions depend only on the initial and final states of the system, not on how that journey occurred. So for example, the altitude difference between Denver and Chicago, whatever that is, it doesn't matter whether you flew between Denver and Chicago or if you drove. The change in elevation between the two cities is going to be the same no matter how you traveled between them. Similarly, if we look at the internal energy of 50 grams of liquid water at room temp, it doesn't depend on whether we got to that liquid water at room temp by cooling off that water from boiling or heating it up from freezing, or not, well, yeah, from almost freezing. It doesn't matter whether we got to that 50 grams of water at room temperature at 25 degrees Celsius by warming up water or cooling off water. The amount of internal energy that liquid water has at room temp is going to be the same regardless. So that's why temperature is a state function. It doesn't matter how you got there. So whether we did warming it up or cooling it off, same amount of internal energy is going to be in this liquid water right here. All right, so a state function does not depend on how that internal energy is used either. For example, a battery in a flashlight can be discharged by producing heat and light. That same battery could be put in a toy car and used to produce heat and work instead of heat and light. Doesn't matter how, that change in internal energy of the battery is going to be the same, regardless of how that energy was used. All right, here's kind of a pictorial version of what we just said there. Okay, so a state function is simply a property that is independent of the pathway. Okay, energy is another state function along with pressure and volume and temperature. Those are all state functions. Work and heat, however, are not state functions. Think back to the hikers taking the two different paths. One hiker did a heck of a lot more work than the other one. So work and heat do depend on the pathway. Okay, those are not state functions. All right, so here's the kind of chemistry-ish questions we're going to have over this. All right, two gases, A and B, are confined in a cylinder piston arrangement like we've had throughout the gas unit. Substance A and B react to form a solid. So as that reaction occurs, the system loses 1150 joules of heat to the surroundings. So since the system loses heat, what sign should Q have? Hopefully you said negative. Then the piston moves down as the gases react to form a solid. As the volume of the gas decreases under the constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. Okay, the surroundings did work on the system. So should W be positive or negative? Hopefully you said positive for that one. So what's going to be the change in internal energy of the system? Well, delta E is equal to Q plus W. That part's not hard. It's just assigning the signs to Q and W that can be tricky. So the system lost heat, so we're going to assign our heat a negative value. And then the surroundings did work on the system, so we're going to make that positive. You put them both together and you get that the change in internal energy, the delta E, is negative 670 joules. So overall, the reaction released energy. More went out than went in. Okay, so this is basically the first law of thermodynamics. Okay, here's another sample problem though. Calculate the energy change for a system undergoing an exothermic process in which 15.4 kilojoules of heat flows, it's out because it said it's exothermic, and where 6.3 kilojoules of work is done on the system. Okay, so that'll be positive because work was done on the system. It's like getting a massage. Okay? So add the two numbers together, voila. Okay, I'm going to stop here before going into enthalpy.